Okay, welcome to Screenaholics podcast episode 14. So, you know, if you haven't already, go back and listen to the first 13 of these. And, it might take some work. There's some of them are divided up. Like to listen to episode 4, you have to listen to there's like 4A, 4B, 4C, and 4D. So, which sounds probably like a math test, which is ironic and appropriate because this episode is the math episode. It was intended to be released on Pi Day, March 14th, episode 14, March 14th, 3.14. But it was recorded on March 13th, and there were some technical glitches, which caused me to delay. I couldn't more than I could fix. And I was super busy because I was going to go to the Man-to-Man weekend, March 15th, 16th, and 17th. There's a technical glitch right there. I dropped the card that I was going to show you. I had to lean off screen, but this is a card about the Man-to-Man weekend, and there's another technical glitch, putting it upside down. But it was a great weekend. It was a powerful weekend, and the next one's in August. So go to mantomen.org and get to your Man-to-Man weekend. The next one's in August. Now, back to this video. Two things going on in this video. One is I have a guest on. It's a repeat guest. It's our guest from episode 2, Dale Holder. He came on as somewhat of a expert in fashion or style, but he comes on now as a math enthusiast who wants to talk about a difficult math problem that was on the internet, part of the International Math Olympiad, which is a contest they give to real smart high school students. They're solved problems, but some mathematicians found a new way to solve this one, including and Dale was intrigued by the problem and came up with his own new way of solving it that he wanted to show. The whole episode comes at you like a Numberphiles episode. If you've ever watched Numberphiles, it's a podcast where they give you some math concept for like a minute. It looks kind of, oh yeah, I can understand that, and then it goes off into something that we definitely cannot understand, and that's what happened in our episode. I think Dale was hoping we figured out in 20 minutes, but it took us more like an hour. So only probably the most dedicated math loving listeners will get through all of this. However, the first 20 minutes are dedicated to the other part of this podcast, which is I am here. This is the first time we've really set our sights on another podcast and sort of are competing with them. So almost like we're running as if we were running for political office and we're doing some negative campaigning. Yeah, I'm coming after you, Bobby Hogwalloper. So this guy, Bobby Hogwalloper, get this. There's this guy, Bobby Hogwalloper, who has created a video that called, as you can see here, Reciting Pi to 1,000 plus digits from memory. Now, so of course I would like to think that I could recite pi to 1,000 digits from memory, and it got me pissed off. Like, why can I, I'm good at math, but I can't do 1,000 digits from memory, and this guy can. And does he think he's better than me? And of course he does. Of course he thinks he's better than me. But I kept watching the video, just stewing in resentment. Like, look at this guy, thinks he's so smart. But I realized something. He might not be so smart after all, Bobby Hogwalloper. So with all your sponsors, we don't. I mean, we're sponsor free here at Screenaholics, except for when we're not. I mean, I don't know. Sometimes whatever. But he has a lot more sponsors than us as well. So we had to take him down a peg, and I think a lot of this video is dedicated to debunking that particular video. I think that's to the benefit. I think that's to my listeners' benefit. A lot of my listeners, we have some of the same. I think our listeners overlap a lot. A lot of you probably are fans of Bobby, and look, he's not I'm not trying to say he's a bad person, but you can't have this video up on the internet and pretend that it's I think I'm just laying this down, and I hope maybe some kind of retraction or apology follows once the word comes out. Once this is like a community note. If you're into the X platform, it's like, hey, this hey, Snopes.com, you might have this one wrong. I'm just saying. So with that, I'm about prepared to have you start watching what was recorded a week ago. But one other thing that I wanted to tell you about before. Oh yeah. So as Dale and I got into it, started talking about 7 minutes into our conversation, there's a reference to Dale mentions, math. A lot of people are bored by math. They don't like the word math, and so and he tried to encourage people, like, think of it as a puzzle or Sudoku. And he said math education is done all wrong, and people's math teachers screwed it up for them. So I wanted to I made me think of this essay, which during their conversation couldn't remember the name of, and I was just like, oh, this is some essay. Well, it's this essay right here. It's a mathematician's lament, or by Paul Lockhart. So maybe sometimes referred to as Lockhart's Lament. And you can see it starts off: a musician wakes from a terrible nightmare. In his dream, he finds himself in a society where music education has been made mandatory. We are helping our students become more competitive in an increasingly sound-filled world. Educators, school systems, and the state are put in charge of this vital project. By the way, my mom's a librarian, or was a librarian, and we like reading to people. So here I am reading too much of this thing. You could read it on your own, but maybe you get the idea that So imagine if music was a required course, but the students don't actually even get to play any music. Like, they don't even get to touch instruments. And then he goes on and gives an example of an art class, and where you don't get to use the paints, or so. And he says math is the same way. Like, these that are primary ed, like K through 12 math students, don't actually get to do any math. They're forced to study the math that was already done by mathematicians in the past. But he says math is creative. These students are just told to basically read the amazing creative things that were done by others, but they're not allowed to really do their own creative work, or they're not encouraged to do their own creative work. And I could go even further into it, but that's not what this whole thing is about. I already went too far into it. Sorry about that. Jeez. Sorry, not sorry. Ha ha ha. Okay, so what the heck? I want to just pardon my profanity, but I just get excited talking to you. There you are out there on the internet. I might know you, I might not, but you're getting to know me. That's fun. I'm getting to know these other people that are on the podcast. That's fun. If you've got an idea for the podcast, hit me up in the comments. Like and subscribe. Join the Screenaholics community. It's a great community. It's not really a community. It's just, but imagine if it were, if it could become a community. As long as they don't get debunked, now that I've taken aim at, I'm trying to rock. This video will rock the Bobby Hogwalper community to its core, I'm sure. Wait, it'll rock it to its core. And with that, I better leave you. So looking forward to whatever happens next, and thanks again for supporting the channel, and have a great rest of your day. Bye. So the last time you were on the podcast, you were here to talk about style. Have you noticed anything new in the fashion world before we delve into a totally different subject of mathematics?
Oh, well, if you remember the last podcast, style and fashion are two different things. Fashion is the, ephemeral trends of the day, and style is a more lasting thing. So I'm not looking out for fashion trends.
Did I say fashion and not style? So style, yeah. What's new in style then? What's
Well,
the classics are still good. The classics
Yeah.
are still stick with the
That's the
classics.
great thing about style. Is just stick with the classics.
The classics are still.
Yeah, you don't need to change your wardrobe every 2 years. Just stick with what you know.
Okay. So well, maybe I don't know if this is true, but maybe we could say that mathematics is maybe it's currently out of fashion, you know, but it's I don't know if it's always in style, but yeah, I was telling somebody we're recording this on March 13th, and I mentioned to somebody that tomorrow's Pi Day, and they said, "What's that?" And I said, 3.14, and they used some pejorative that I'm not going to repeat on the air, but it's a 4-letter word, and so. But I don't know what is what is so yeah, happy Pi Day, and what do you what do you think? Any thoughts on most memorable Pi days in your, or any stories about pie that you want to talk about on this?
We just got an email that was sent out at our work that we're going to be celebrating Pi Day, and the secretary sent it out. And
really?
She said, well, the patron saint of pie is going to come deliver them at 1:30 tomorrow, so get ready to eat your pie. And of course I had to insert a snarky comment. I said, "You're being irrational, Bernadette. The patron saint of pie is Euler." And in fact, he was one of the people who popularized the use of the Greek letter pi in reference to the ratio of the circle. The guy was
Euler. Yeah. I mean, I know about Euler.
Mm-hmm.
So I just changed the. I just put broadcast our feed onto. Okay, and that works. Okay, good. It's fixed, so you can. All right, technical bullshit. Technical stuff isn't supposed to distract from the. But we did this so we could actually play some videos. We want to play some videos. Okay, and you've got a whiteboard, so we're ready to do some math. So you're ready to do some serious math over there.
Serious? No, not serious. Math shouldn't be serious.
But
we don't want to discourage your viewers.
Well, did I cut you off on the Euler subject? Were you running somewhere with that, or you pretty much?
That was the extent of my Wikipedia knowledge that I looked up. Yeah.
Okay, so yeah, let's so for Pi Day, well, let me if I may sort of start us off with a little like a hors d'oeuvre before the main course that you've got with the. So actually, tell us what are you gonna, what math did you bring here today? To talk about. You've got some, you're gonna fill that whiteboard with something. So just give us the sort of a preview before, and then maybe I'll distract us, and then we'll get back to it.
Sure. So there is something called the International Math Olympiad. And I know you like to follow sports, and this is like the Olympics for math. And there's a number of high school students who participate internationally, and some big names have all been to there, like Terrence Tao.
That's
popular name.
It's the big name in math. I think it's the only one. I think the current one.
Yeah. Well, he won the Fields Medal, which is the Nobel Prize in math, given out every 4 years. And he was there in 1988, and we're going to be doing a problem from the contest that he was a part of, and he did not get this problem. Only 11 people out of like the hundreds that were there were actually got this problem like fully correct. Now, to be fair, Terrence was like 13 at the time, so, and everyone else was in high high school, so we'll cut him some slack.
Okay, this is not related to the $1 million problems.
What, like an open problem?
Right.
No, these are solved problems.
These are solved problems for the competition, these are fun competitions. We have some, mathlete competitions are cool. Sometimes they have individual. You're working as individuals, and each person just works on each problem for 5 minutes, and they put the answer in a box. And then there's a group problem sometimes, so teams can work on them together.
Yeah, and just for your listeners, if your eyes are starting to glaze over right now because we're talking about too much math stuff, a lot of people. I'm a math major, and people always say, "Oh, I hate math. I'm really bad at it." And I always say nobody's bad at math. They're only bad math teachers.
What a cruel turn to math against math teachers.
Math is actually fun before school kind of sucked the life out of the subject. So we'll try and think of it like a puzzle, like Sudoku or something.
Pisses me off that I forget the name of the essay, because I was just thinking about it recently, but there was like a 20-page essay. Like, my cousin, like a much younger cousin, like recommended it to me a while ago while I was teaching, and it's by a mathematician talking about exactly like how screwed up the math curriculum is. He makes this analogy about how it's as if, like, if you were going to become a painter, but they're like, okay, you're going to become a painter, but we're going to put you in an art school, and you can't use any paint. You know what I mean? You don't paint at all. And maybe eventually you get to paint, but only it's paint by numbers, and you have to only paint exactly where you put the blue where the blue is instructed to be, and the red where the red is instructed to be. So it's like this, terrible. So it's like, imagine this nightmare, if you will. And he says that's basically what happens with math. Like the stuff we have students doing is not math, and it's not making them like math or making them learn math oftentimes.
Well, I'm not a math teacher, so I wouldn't speak on that.
Me neither. Anyway, all right. So that's coming up. The what's that problem called? Does that have a name?
Yeah, it was a relatively famous problem. It's question 6 from the International Math Olympiad 1988. For a while, it was like the hardest problem that they had ever given at one of these.
Question 6 from the International Math Olympiad.
There's been some harder ones apparently that have come after it now, but this is definitely still one of the hardest ones.
Okay, and there we have. Okay, this is now before we do that, I want to debunk. So before we do that, problem 6 from the International Math Olympiad, I'd like to debunk a video currently online. Now, so this video online is, I think it's called Bobby Hogwalloper recites pi by memory while driving in the Highlander.
Oh, did he miss a number?
Well, so I'd like to.
For shame.
Let's look at the tape. So here, let's see if I can get cut to this here. So I'm gonna transition here, and this is some other work by Rob Hogwalloper. I think you can see this on the screen here, hopefully. And but if I go to his account, it's got 1.52 thousand subscribers, and here it is, reciting pi to 1,000 digits of memory. So
hey folks, welcome back for another episode of Math in the Highlander. This is a Highlander, and I have a passion for math. 3.14159.
Highlander.
Okay.
I know her.
Okay, so we see there that the 3.14159. We heard that much. No problem, right? I mean, you agree. We agree so far. That's right. But then then we want to go to some other sources. So we should let's go and look for some of these other sources to look up pi in. So actually, what I think I just asked Google, what is pi to 500 digits. I didn't even get to past. I think maybe let's do 1,000. He claimed 2,000, right?
1,000.
Let's check the first 1,000 digits of pi. So there we have this. Okay, so I took that, I copied it, and I pasted it over here into this document. So, well, you see two numbers here. These are different numbers. So they start off. They both start off 14159265535. But then this one says 8979. But this one up here says 89813. Now, wow. So let's go back and check. Let's check the video. See which one Bobby Hogwalloper is saying. Okay. All right. So here we go. So far we have 3.
If there's anybody worse than a guy reciting pi in his car and posting it on the internet, it's somebody correcting him on the internet.
Well, worse. I'm not sure how I'm not sure about all that. But anyway, let's go back to the tape here, and see where we're at. We got
3.14159265358981381346.
Okay, so 8981346. So that must be this one up here. It looks like there it is. But down here we have, 89793238, and I think you'll find that to be the case right here. We have this right here, okay. But then, so actually if we go back to the video for a minute.
2679.
Okay, so then it says this recitation has been verified by Snopes.com. So
yeah, and we all know that they're bastions of the truth in the free world.
Well, I mean, well, I don't know. I mean, yeah, I wonder how Snopes.com got dragged into this. Because
it looks like he copied and pasted the Snopes graphic and used the same text as before with the Highlander.
Well, and again, it could be, it's Snopes.com versus Google.com, right? Like Snopes versus Google.
He couldn't even use AI for that fake. That was a shallow fake.
I could use, but
1, 2, 2, 5, 3.
Maybe the thing. If we could just watch a little more of this, and what I'm wondering is if we could watch a little more of this, and if I could actually identify the part where I figured out. See if you can tell where I figured out how that maybe he was incorrect in some of these.
I would, but I'm having a hard time hearing because my ears are bleeding.
Okay. Great. Okay, it's good. Well, there's a first aid kit in the other room. All right, here we go.
4.
Oh wait,
6,
I lost. Oh, there it is. Okay.
7.
Okay, here's an idea. Can we come back to this? So, I think, because I do think that there's more there, but I think we've had a little bit much for right now. So maybe we'll come back to this. You may want to leave before we get to it. But my contention is there's a part where the actual numbers are like there's a part, I don't know, maybe
and my contention is that there's way too much dependence on Ambien when there's videos like this out on the internet.
So as long as Bobby Hogwalloper is I mean, I do hope he sees this video. I do hope he sees this video because but I have emailed him before. Apparently he lives in Iowa. I'd try to have him on the show, but yeah, that listen while you walk to work song I was playing. also by him. That's his work as well.
Okay.
And it's the only
an instant classic.
I have and I try to inflict that song. I have a job where I get to choose the music in a room, and I choose that song. It's called Mood Boost. And
where's that job at?
Listen.
Guantanamo Bay.
You're supposed to listen to it for an hour every day for amazing results in your life.
Nice.
Anyway, okay, so let's talk about the International Math Olympiad problem.
Okay.
If that's set up, can you follow that?
It's a tough act to
How
follow.
do you want to get into this? I'll just tell me about it. And you got,
Okay.
it almost looks like you have two whiteboards there, but
I do. Yeah.
yeah, you do. All right, that's why it looks that way. All right.
Yeah. Okay. So all that suspense for the question. What is this question that the future former Fields medalist had a struggle with?
Yes.
And not to mention some of the mathematicians who were adults there couldn't
Yes.
do it in like 6 hours.
Yes.
I would be remiss if I didn't mention that my current teacher, Professor Zvezda Stankova, did solve it, and it launched her mathematics career. And hopefully we can link that video of
which I did not.
She made a video where she actually described the common solution.
Should we pull it up now or later? Later.
Yeah, later. It's fine. Yeah.
Now and later.
Well, you should probably find it. If we should fast forward, and it's kind of it's like when you watch it, it's like watching the guy in the Highlander. It's almost impossible to follow at first glance.
Well, let's see. Can I get a new tab in here? And then what? So I look up.
IMO question 6.
Okay, IMO question 6. And then the legend of question 6. Wow. Okay, so it's me a week later, and the video, even as I record currently a week later, is not up on the internet as of this moment, because it's confusing, but because it's confusing whenever you record anything, especially like an answering machine message, or you're time traveling when you record something. And so as I speak these words, it's the past for you who's listening to them, and I'm talking where you're listening to them. That's the future. So that's time travel, and that's true of writing, reading and writing, any kind of recording. Having said all that, I want to. Oh, here comes Felix trying to jump into my lap, but he's still alive through thick and thin and calamity. We had trouble with screen grabbing and screen capture, and so I was going to try to show you. Dale and I were going to try to watch that live together and just include that in the interview, but it didn't work, so we're going to try again now. I'm going to show you my screen now. Go over here. This is the video that he wanted me to see. The notorious question 6, cracked by induction. It's a Numberphile video. They point out in there that they have plenty of other videos about question 6. There's one. So what I'd like to do is just sort of fast forward. Oh, and that might be the problem. Let's see if I'm still recording. I appear to be, but certain keys, if I press too many keys, sometimes they'll stop recording. That might be what happened last time. But anyway, you see, here she is talking about, she was like Terence Tao, the Fields Medal winner. She was at the International Math Olympiad in 1998. And she actually got this question right, and Terence Tao did not. They're both math professors. There she is. There's another fellow named Emmanuel something who also got the question right and did it in some revolutionary way. And so she's talking about it, giving an introduction. There's the problem, number 6, at the International Mathematical Olympiad in Australia. And basically they're asking that this very, very kind of niche question, this idea that AB plus 1 does not always divide A squared and B squared depending on what A and B are. But if it does, the division has to, like, the answer has to equal the square of an integer. It has to equal 1, 4, 9, 16, 25. It can't equal 2, 3, 5, 6, 7, 8, 10, 11. So weird true thing, and you can prove it. And this mathematician set out to prove it, I mean, all these, it was proved a long time ago, but this mathematician did come up with an elegant proof of it, and she has a 28-minute video of it here. And Dale wanted us to not watch the whole thing, but rather watch enough of it to show how long it is. So I'm just gonna do some more fast forward. Let's see if I'm still recording. I do appear to be. Keep fast forwarding. Look at how long it is. It's a very involved proof. Very involved. There she's actually giving some examples when she puts numbers in there, but lots of variables, lots of algebra. And so the setup here is that Dale figured out a way to make this less overwhelming with the algebra, and it's more visual the way he's going to show us. All right, so I hope this transition helps and that you are enjoying the video, and here comes some more right now.
Are you ready for this, Darko? This is pretty involved proof.
I mean,
this is not for the faint of heart. Or the faint.
I'm gonna cut you. I'm gonna cut you off at 11:30 or so.
Okay. Well, did some of the viewers see the long, laborious algebra in that other video? I hope that they would see that as a contrast to what I'm about to do.
Okay, good. Yeah, it was especially not. I mean, we didn't go that far in the Numberphiles video, but just where I was fast forwarding through that, video before that, we saw a lot of writing, right?
Right.
So I mean, you want to do it? Well, yeah. So yeah, I think we got. But I think so our viewers, Dale's asking our viewers, are you ready for this? Get out a piece of paper, stop just writing this, acting as if you're going to remember this. You need to sit down, I mean, okay.
This is the math teacher here, okay? Sit down, kids. No, I think that the previous video explains it very well. It's an elegant solution, but it's purely, mostly algebra.
Okay.
And so what inspired me to do this was this problem was given to me, and I was having a hard time visualizing it, and that's mainly that's kind of how I like to solve problems. And I was thinking of how can I visualize this? There's a number of interesting proofs. You're familiar with the visual proof of 1 plus 3 plus 5 plus ... 2k plus 1 is equal to k squared, right?
So, the last one is 2k plus 1. So for example, let's just go 1 plus 3 plus 5 plus 7
is 16, which is a square. So 1 plus 3 plus 5 plus 7, 7 is the fourth number in that. Is it a sequence or a series? The fourth number, so it's 4 squared.
Because that 2k plus 1 confused me into thinking that the 7, since 2k plus 1, if 2k plus 1 is 7, then k would be 3, right? So should that be 2k minus 1 maybe?
You got me. Yep.
Okay.
You're absolutely right.
Okay. Sorry. but that makes more sense. But then that just helps me see it. So yeah. So then. So now it's okay. So yeah. So.
Okay, but my point is that there's a pretty nice proof of this. Here it is.
A weird technical thing has happened just as you're doing that, where a weird thumbs up has started to appear on my screen. It happens every once in a while.
Oh.
I'm like, at least it's not thumbs down. That's what I always.
Are you trying to like make people
weird
subscribe?
It's like
ring that bell.
It's literally like a white.
Like
you can see it on this. A little white thing popped up. It started doing it when I interviewed Justin Chimino for episode 11 or 10. No, it's 11. That was 11. This is episode 14. Is in 3.14. All right. So you're using a visual something or other.
Yes.
Okay.
So this is 1 plus
3 plus
5
all
plus
right.
7
And geometric
ends up being 4
yeah,
squared.
Cool. Okay. All right. So the geometric illustration of the algebraic sequence, and that's like a sequence shortcut kind of, right? Or not a sequence shortcut, but like maybe it's just called a sequence formula. Those are like, you learn things like that. Where like, oh yeah, it's a formula that gives you the answer to those sequences or something.
Mm-hmm.
Okay.
Sure. Yeah. One of them, another one that's pretty famous is. Got an eraser here.
I've got Kleenex.
No, I got one. Yeah.
We both have we both brought whiteboard erasers.
This is the Pythagorean theorem. Come back to haunt you. And
that created by Pythagoras, and the Pythagoras was like a math god, or like he had a cult.
Yeah.
And people followed him because he came up with this theorem.
Yeah.
Thumbs up.
Thumbs up to cults. So this is c squared. If you actually extend this here, am I doing this right?
I have done there's a one where you can actually fold paper and do it like it's
yeah, there's this one where you have the squares connected to the triangle.
But that's not the point. The point is to show there are visual proofs to algebraic that coincide with algebraic proofs, and you've got one for the IM.
Yes, for the IMO.
IMO 6
geometric proof.
Okay.
All right. So what is the problem? You have prove that if a b plus 1 can divide a squared plus b squared, it will equal a perfect square.
Coincidentally, maybe only coincidentally, a part of the Pythagorean theorem is kind of in there?
Yeah. In fact, that's what kind of got me
Led
thinking
to the
about this. Is like
geometric
I can
proof thing. Okay.
I can visualize this. It's squares. I like squares.
And this is
My,
kind of what we were referring to earlier about how in school they don't let you do real math. Like what you're doing here, that you came up with or something, is real math, right?
Yeah. And this, I tried to find like a visual or a geometric proof, and the only thing I found was like a graph with hyperbolas on it. I don't think anyone has done this before.
Most people think that you just are saying that you found a graph with a lot of exaggerations on it. Like a lot of tall tales. But that's not what you're saying really at all.
So a squared plus b squared is divisible by ab plus 1, and we need to prove that this number, this positive integer that is the quotient, is always a perfect square.
Okay.
And to do that, I figured we should convert these into polygons and then try and find k as a square.
Polygons, you say?
Yeah. Quadrilaterals.
Let's introduce.
Yeah.
All right, we got.
Okay, so a squared plus b squared, that's simple enough. It's just a square a. Oh, also, it's important we do have to do an algebraic step. We'll just multiply each side by ab plus 1 to bring this over to the other side.
Okay, so soon we'll start this geometric proof, but first, a little algebra. One concession to algebra.
Okay. Now, in the problem, you're given that it's a and b are positive integers.
Uh-huh.
They could equal each other.
What's an integer?
Hell if I know. You're the math teacher.
Unfounded accusation. I don't know.
It's an integer is a whole number.
Okay.
Yeah. So
Whole number. So like one.
so
two,
those
three, four,
also includes the negatives, like
five.
-1, -5, etc.
But not fractions or decimals or pi.
Yeah. But you're counting
There they are.
numbers.
There they are. There they are.
Your natural numbers, but -0. It's a 1, 2, 3, 4, etc. And
So A and B are whole numbers, but they could be anything.
yeah.
Zero is an integer, but they're not zero, right? Or, could one of them be zero?
Could one of them be 0? Maybe.
That's not the case for like this many.
Not according to the question, but
Okay.
it might be a 0.
Okay.
Foreshadowing.
Okay.
So ab plus 1. So we have a here. This is a squared
B squared
plus b squared, and then k times
Heck is
ab plus 1.
So AB is a rectangle. So these
Yes.
A and B are squares. AB is a rectangle.
Yeah, there's a rectangle with a length and b width. We'll just go like.
And then 1 is, I guess, it can be
And then we'll just put
represented as a 1 square unit, but it could be
Yeah.
any other. It could be
just
like
put it up there. Can
okay.
you see that?
Yeah.
Oh, there's a thumb.
There's the thumb. You see it. You see it. Yeah.
Okay.
Somebody, some AI is watching and approving.
So whenever you multiply something by a number, which is k in this case, you're actually just adding k of them together.
Okay. Yeah,
Yeah.
that makes sense. So, what he's saying, for the folks at home, is that like 5 times 3 is actually 5 plus 5 plus 5, or it's 3 plus 3 plus 3 plus 3 plus 3.
Yeah. So we have
a bunch of, so you're drawing a bunch of those AB rectangles that you made.
Of these, but we don't know how many.
Okay, but we're adding them together.
Yeah. And then all these little ones right here, that adds up to k.
Those get added too because the k multiplies both the AB and the 1.
Yeah.
Oh, but there are, since it's 1, there's k of them. Okay, yeah.
Exactly.
All right.
Yeah, so we want to be able to combine all those
They add
rectangles.
up to k. 1 plus 1 plus 1, k times equals k.
Yeah, but to make this like
times k equals k.
To make this a combined rectangle.
1 times k equals k. K.
K, you got it. How do we put these all together if we don't know what the lengths are?
Put them all together. We don't know what the lengths are.
Yeah.
How indeed.
How indeed. Well, there's a couple ways, 3 ways you can do it actually. There's case 1, 2, and 3.
He's writing case 1.
So case 1 is we make a.
Maybe you should be using the bigger whiteboard, then you can draw bigger.
Okay.
But it's
I'll switch over in just a minute.
Okay. There's a weird thing going on my screen where like the microphone and the screen it like cuts. It's vertical and it cuts right here where there's a mirror against the wall, and it looks like there's almost 2 shots, but it's really just one. I'm gonna move the microphone just to fix that disturbing notion.
Okay.
Back to you. All right.
One thing I didn't tell the viewers at home is that
This is a palatial estate.
yeah. You can. We don't know if these are actually different numbers or the same number.
Got it. They could be the same number, but they're probably maybe they're different.
As an exercise at home, you can try and make them the same number. There's only one number that satisfies that. It's 1.
That's the only way you can do it where it's the same?
Yeah, 1
Okay.
squared plus 1 squared equals k.
Well, and K is 1.
Yeah, and k ends up being 1, which is a perfect square.
Okay.
1 times 1. And if you try and do any other number, let's just be like 2. 2 squared plus 2 squared is
4
8.
plus 4 is 8.
Yeah, and then this
4
is
plus 1
5.
is 5.
So 5 times k equals 8.
Not if K is a
Yeah.
whole number, which it has to be for this
Yeah.
part of this thing.
Yeah,
Right.
and on, and there's
Won't work for any other squares.
Won't work
Okay.
for any other number. That's this. A and B have to be if they're
Different.
Not 1, they have to be different. So, but in this example, we just assume that these are just variables. So we'll just make B larger. And
Okay.
Yeah. All right. So case 1, we combine all these, and it's a little one.
A little
And-
one.
Yeah, a little rectangle. And then we can also combine all these, and it ends up being a square. And then, or we could combine all these, and it ends up being a rectangle with a larger width than height. So that'll be case 1, case 2, case 3.
A larger. Okay, so when you said a little one, you meant with a smaller width and height.
Yes.
So the A times K is less than B, A times K equals B, or A times K is greater than B. I'm surprised at that. So it'll be interesting to see why that distinction is important. Right? That'll be interesting.
Yeah.
Ah.
Well, we have to try and consider all cases because we don't actually know what the numbers are, and we're trying to generalize over all of these possible values.
So visually speaking, that those when you're as you're trying to figure this, you're thinking of those. Is K plus 1? Is the plus 1 gone from our analysis for right now?
That's a good point. No, it's there. I mean, it'll still be there, but it's not going to change.
Okay.
You can draw it on there, and then it'll just be K, but it doesn't affect the size.
All right. Case 1, 2, and 3.
Okay, so I'll switch over to a larger board. All right, case 1. This is K. So we don't actually know. So when I draw this out, it looks like there's 3 rectangles there, but we're generalizing. We don't know if it's 3 or 300, because we don't know what A and B are or K. So let's.
Are we doing case 1 here?
This is case 1.
All right.
Thanks for.
Let's get into case 1.
So let's just draw it without all those lines in the middle, because we don't know how many there are. But as you said, B is actually greater than K times A.
You know what we could do is we could stand up and walk around with these microphones, and then I could just hold it out to. I could hold your microphone and stand over within the camera. I don't know. Then we wouldn't have to.
Okay. Well,
it's a possibility. Just think about it.
I'll let you think about that. Whatever's best.
Okay. I might wander into your shot here with my microphone. But then here, what I could do is maybe this would help. Is I could just turn the microphone. Like if I hold it like if I hold it like this.
Okay.
Because then that's because it gets. You know what I'm saying? It's like yeah. There we go. There we go.
Okay. All right. So remember, we've still got all those K's, and this is equal to A squared plus B squared. A squared, and then we've got B squared. Well, this looks pretty similar. Yeah, and
It's interesting. It's AK plus K, right?
yeah,
B times this is AKB plus K. All right.
yeah. But this actually has the same height, right? And then so B is greater than K. I mean, I spent like hours playing around drawing squares to come to these simple conclusions. But
B has to be greater than KA. We know this. Wait, why is that? Is it because it's case 1? That's what
it's case 1. Yeah,
okay.
yeah.
B is greater than KA. All right. B the height.
So
okay, got it. Sort of. All right.
So if we were like, you know, if we were just comparing things in an everyday environment, we could almost like look at one or look at the other and just kind of weigh them in our hands. And it's kind of like we're doing this with a scale here with the equality sign, and we can compare this B square to the B because it has the same height. And since B is greater than KA, if we were to compare it, we'd find that one is larger than the other. And so if you projected, or if you held these together, these two shapes, this square would be larger than this rectangle. And you'd have like this gap here, this extra space. And then, so if this was there, this sort of like shadow here of this projection, that means that A squared, you basically need, this K has to equal A squared, but then you also have to have enough K to go in here to fill up that void.
K equals A squared?
K would have to equal, it have to be greater than A squared.
It's greater than A squared. That makes more sense,
Yeah. K would have to be greater than A squared. So it could have enough area to fill up the A square here, and also fill in this gap here.
Right.
But wait a second. You're following this, right? Like the when you're kind of comparing these two, it's tough to follow because I made this sort of projection that's not actually here. But when I'm trying to compare the two, basically I'm putting I'm basically like putting this on top of it, or vice versa. If you put the B square on top of this, there's a it goes over it and too much.
It's so weird. Because we're definitely saying that BKA doesn't even matter what case. BKA plus K equals A squared plus B squared in all our examples.
Yes.
It has to be true.
Yes.
But then, and therefore, because, well, so we're gonna have some cases where this rectangle, the KA is it's just sometimes going to be true. The KA is less than B. That'll make sense. When that's the case, the amount smaller is this thing that you shaded in.
Yeah.
Plus
and then so this K has to equal
minus K, kind of.
Yeah. So this K has to be large enough to fill in all this area, and then also be greater than A squared.
Okay. I guess that makes sense because. I think that makes sense. Okay, continue.
Okay. Well,
part of math for me is like you have to be able to. You can't just wait. You can't be like, oh no, we're not going to go forward until I totally get it. That's like it's like I'm not going to believe in a faith or you got to keep going even.
Maybe it'd be better if I projected it on the other side. So like, I haven't tried that. So what if I just projected this right here to be, that usually helps. This right here is K times A. Yeah, this might be easier. The whole deficit thing is tough. Okay, let's compare the K times A times B rectangle to the B square. This is where it would actually fall onto the B square in the shaded region. That means that K, this is a better way to explain it, K has to, this is already accounted for.
Use that up. Okay, so K is greater than A squared plus.
Yeah. So what you have left, this has to go in there. This has to be enough.
K cannot equal A squared. K has to be greater than A squared.
Yeah, K has to be greater than A squared, and then it has to fill up this space right here. But wait a second. We know that B is greater than K times A. We know that K times A, because these are positive integers, that's greater than K. So even if you just had K and there weren't even any in there, it would fill this, even if it was like one width rectangle here, just one little area, you couldn't even fill this up.
K would not fill that.
Yeah, so it's a contradiction. So
what's the contradiction?
The contradiction is that
for B to be greater than K,
if B is greater than K times A,
then B is greater than K.
Yeah, B is greater than K. But K, these are only 1 by 1 Ks. Mm-hmm. So when you're comparing these and you put these all here, they can't even add up to B. So not only does it have to add up to B, the length here, it also has to fill in this A square. So there's no way that it can do that.
Why can't the K's add up to B? Because of this?
Because
B is greater than K.
Because in this case we assumed
B is greater than KA, and therefore B is greater than K.
Mm-hmm.
If B is greater than K, then therefore the K's cannot fill this out. So therefore we have a contradiction. Therefore there is no case 1.
Exactly. No case 1.
There's no case 1. By the way, so just interesting. I'm just noticing the type of video we were making with me over here now. Talking to you mostly off camera is a very Numberphiles video. Watch out, Numberphiles. What's that guy's name who does the background? Sandy is or some guy.
Brady.
Yeah. Brady. Watch out, Brady.
I'm coming for you, Brady.
All right, so let's move on, I suppose, to case 2. Or perhaps case 3. Or as Brady would say it, well, what about case 2? British accent. Well, why is that? Well, that doesn't seem right.
Yeah, let's make fun of English people and their accents. We don't know geography. Where's Sophia at?
That's so racist. It's a popular thing now to have like a British AI answering machine. You know, it's like, oh, hello, the person you're calling is not here right now. It's totally racist.
We have no politics here in math. Thank goodness. Okay, so case 2. What are we doing? We're trying to draw a square. We're trying to compare these two things.
Did a bad job at
Remember, a squared plus b squared equals k times ab plus 1.
All right, so we're trying to keep trying to push that board back here. That's probably why I'm over here, is to get you to keep you
All right.
flat with the camera there.
Case 2, let's assume that k. No. Let's assume that a times k is actually equal to b.
I mean, I think English people are okay. You know, I mean, they're not. You know, I don't have any.
Okay. Sounds like you got some white guilt over there. Okay.
I like a spot of tea sometimes. You know. Norm Macdonald had like Jimmy Savile or some British guy on his podcast, and he kept saying, he says to Adam Carolla, or no, Adam Egget, he says or he says to the guest, why don't you get some of your mates to go over and do something? And he says more normal people call them friends, but they call them mates. That's the anyway. Felix is sitting on the microphone cord.
Okay. All right, a squared plus b squared equals kab plus 1, which when
Now it's a square. Case 2.
Yeah,
Square.
a times k is equal to b, so yeah, it ends up being a square.
Okay, I just had a premonition of where this is going. You're going to negate this too. Is this going to be impossible for all 3 cases? All right, let's just some pondering. Okay, so let's see if I'm right. My premonition is correct.
Don't monition too hastily now. Okay.
All right, slow down.
Keep your
Slow down, Brady.
Yeah. Well, there is something interesting that happens, but it's not a contradiction. So this square is actually equal to this square.
Because it has it's b.
So
B's the side and it's the square. So
yeah. So let's just subtract them from each side. And what do we have left?
A squared has to be 0.
No, because don't forget about this. All those plus 1s.
Oh, and the plus 1s are so k is not 0. But you said a squared equals k.
A squared equals k.
Now is that okay? A squared to equal k. That just means and k squared equals b. Right? No.
No.
That's weird. Okay. Go get here. You. All right. I'll stop shooting wildly at the.
No, it's okay. A times k equals b. A cubed equals b.
Got it.
Yeah.
I knew there was something like that.
So this is really nice. This has worked out really well. We just had a direct correlation for case 2. All right, case 2.
It's okay. We did not.
Yes.
We did not. Case 1, we found a
Contradiction.
and we basically said there is no case 1.
Mm-hmm.
But there are case 2s, and in them, a cubed equals b.
Yeah. That's a corollary of a squared equals k. Is that a cubed equals b?
Because if a squared equals k, we plug that in up here, and this is k squared times k equals b.
Yeah, and we can even choose any number, cube it, and then put it into our original equation, which was a squared plus b squared divided by ab plus 1 equals k. And let's just check that. So let's pick, can't use 1, But
So
we could. One would work, but it's not interesting.
A cubed.
Yeah, let's use 2. Then what's 2 cubed?
Be 8.
So a squared plus b squared is equal to 4 plus 64, and then divided by 16 plus 1, which is 17. What does that equal?
Oh, yeah.
What? What does that equal?
Well, 68 over 17.
Yeah. It just happens to be 4.
Ah.
Okay.
68 divided by 17 equals 4. 17 times 4 is it. So this whole fraction is a whole number, 4k. So all right, good.
Yeah, that's a perfect square.
So it worked.
Yeah.
Okay.
Which we
now surmise there are other versions of this too. Those are the only there are infinite other versions of that.
Yeah, you could pick
Number,
any
cube it, and then for the other number, and then
any positive integer.
So I hope we can rule out case 3 also. Let's see.
That would be awesome.
This episode is, well, we're brought to you by the Man to Men Weekend. Man to Men will talk about the things men men talk about, the way men talk about things that are important to men. It's happening March 15th to 17th. Go get it.
Okay. So case 3, we've got a squared plus b squared is equal to some rectangle. This one is actually wider than it is.
Longer than the height.
Yeah.
So AK is greater than B. And that's AK on the bottom.
And don't forget that this is made up of a bunch of A times B rectangles all smushed together.
Yes, K.
And each of them, have a 1 plus 1. K of them actually, K plus 1s.
Crazy plus 1, yeah.
Yeah.
Imagine that if you were being invited to a wedding and they said, how many plus 1s do I get? And they said, K plus 1s.
Yeah, unbelievable. That would be a tremendous drain on the open bar. So there's a sub. This actually can be divided into 2 sub cases. One is just like a super long. What if it's just let's just get it out of the way. What if it's super long like that? Well, it can't be too long because if we just compare it to b squared, all this extra area here, that has to be equal to a squared, and that's just way too much. So it needs to be closer. What if it was even like?
So but basically if it got to be the level of 2b squared, if like it was doubling b squared, well then by definition that would be that would mean that a squared. Wait, so what's the problem with it being too much? I mean, I don't understand what you just did with we erased it if it was big and wide.
Yeah. What if it?
What's the problem with that?
Doesn't this side look larger than this side? Because I've drawn B.
But you just drew it that way.
Yeah, I did.
That's math, folks. Say that.
Well, if this is an equality, so if you set A an arbitrary number less than B, then
that thing is AK.
it can't be larger than A plus B, because
what if K is really small? I don't know. If K is really
it doesn't even matter because K is already extra.
K can't be really big, and that explains how wide it is. Okay, so it's like A is smaller, but K is really really big. So we've got a really really wide thing because K is really big.
Yes.
What's the
But,
problem with that?
well, here's the thing, is that K times A cannot be greater than
In this version,
B plus A.
So K times A is greater than B. That's part of the rule in case 3, right? K times A is greater than B.
Absolutely.
But it can't be greater than B plus A.
It can't even be equal to B plus A.
Why can't it rise to B? So
Okay. So this would be this whole, if this rectangle was this big, it would be larger than K. The K times A would be larger than B plus A. Well, let's just say it's just B plus A. Okay. So you've got your B squared right here.
Oh.
So
I'm seeing it. Okay.
yeah. And now you've got the
A squared.
You've got the A squared.
And now.
What's all this doing?
Oh. Huh. Yeah. What is all that doing?
Yeah. So
So
you've got your B squared
big.
here.
Uh-huh.
You got your A squared here. Well, you've gone too far because there's still all this extra area that makes this inequality not incorrect.
It can't be accounted for by these little K's up here?
No, because they're positive ones. Yeah. 1 by 1 blocks.
We just fill with a lot of them. We just make a lot of them and put them all in. I'm serious. I don't understand why we can't do that. I mean, I kind of don't understand why we can't do that.
Okay.
Yeah, A squared plus B squared is equal to K AB plus 1. This is the KAB plus 1.
Okay.
I guess I'm kind of convinced. I'm definitely kind of convinced. Let's keep going.
You're kind of convinced? Okay. Well,
Kind of with a K.
okay. You're kind of convinced. Yeah. So, actually, if this has to be... Remember, we're trying to determine how wide this thing is. If it's too wide, well, then it just won't satisfy the equality because it'll be too much on the right side than the left-hand side. In fact, if it's too wide, even just to like where A times K is equal to A plus B, you'd have the B squared, and then you'd have the A squared, but then you'd have all that extra there. That would be the right-hand side plus the K. We're not even counting the K. Plus the K would be just larger on the right-hand side than the left-hand side.
Okay.
So what yeah.
Okay, I see what you're saying. So the K doesn't fill in it.
Yeah.
It becomes more of a problem. The K becomes more of a problem. Okay.
Yeah. So what actually happens is, this K times A can be larger than A. When I initially saw this, I saw
it's larger than B. So
yeah, that's what I mean. Yeah, it has to be larger than B.
But
it can be larger than B.
But it can't be larger than A plus B. Okay.
Yeah. Okay. Remember case 3. So if it's in between these two things, then it pretty much splits. It's close to the edge there. And remember that we're putting together a bunch of these rectangles. A width and then B length. We're putting all these together. And then when we combine them, this B is actually going to split. It's going to split this very last rectangle of A, B.
Uh-huh.
So this is the most tricky part. Case 3. So case 2 was a ball. We like that. It was really easy to just follow.
Yeah.
This is gonna get complicated.
Yeah. Why are we splitting, anyways?
So why are we splitting it? Because the process is
Trust the process.
yeah, trust the process. We're projecting the b square onto this to compare it. And then so this remaining area, the sliver here of b length plus the k ones has to be equal to a squared. Yeah?
All right. What does the split look like? I mean, like, you notice you heard the word split in quotation marks.
Yeah.
What's the
Basically, there's a remainder. So,
oof?
yeah, I know. We're talking about squares and rectangles here. How can you have remainders? Let's just subtract b from each side. That'll make it easier. So, we subtract b from each side. You got that, Felix? And we have this remainder. We'll call it of length r. And this is length b. And we still have all these k's.
R is what's left after we took away b squared.
Yeah, so we have this remaining width of b length and a bunch of k and the a square.
So it's by however much k a is greater than b is the r, sort of, maybe.
Exactly. Yeah, so it has to be, so this remainder is less than a.
Just a word to our, audience, the people in our audience that don't know what the hell we're talking about. Get it together.
Yeah, think about your life decisions. You shouldn't have been thinking about booty in 8th grade algebra. Thinking about the girl in front of you.
We're just insulting the few people, the imaginary people that are watching.
Okay. So it seems that we've reached an impasse because these don't really give us much information or seem to fit together in a meaningful way. You have a bunch of random 1x1 blocks of k. A b, okay, we know it's length b, but we don't even have b squared on that side anymore.
br plus k equals a squared. Yep.
Yeah.
Okay. Have we split yet, or are we about to split? Is that the?
So this.
Are you setting the stage for the split?
The split was. Remember?
Oh, we already had the split. No, what a bummer.
This was composed of a times b rectangles, and in our previous example, if it was like a full length a, you couldn't have a plus b length. So a times k, when you compare it to b, it actually splits that.
R is less than a.
Yes.
Why does R have to be less than a?
Well, it just has to be. Because if you had a full a,
Yeah.
you would have a times b. I should. This is helping me because I think I should just subtract it so you can see. Instead of trying to project it, I'll just subtract b, so you can see that. Okay, Darko, if we had an a times b, which we can't have because that would be a. It would be b squared there. You subtract b squared from that side, and you're left with a times b. And an a squared on the other side. That's why it can't be a full a. It has to be less than that.
Because now the right is bigger than the left.
Yeah, because a squared is just like.
B is bigger than a.
Yeah, it's just right there, and then it's just all this excess. So it has to be less than that. So you split.
Okay, so R is less than. Okay, got it. Got it. Okay, cool. R is less than.
Yeah.
R is less than A.
Yeah. Okay.
I wasn't speaking into the microphone, but I acknowledged that R is less than A.
Yeah.
I'm having a lot of trouble speaking to the microphone.
Viewers, you might want to take 5 and think about just what the next step is, because I need to get some more cookies.
You're gonna take 5?
Just so you know, in the International Math Olympiad, with all of the best students from across the world, they have 90 minutes approximately to solve this problem. So we're doing it in like 20, which is pretty fast.
By 20, you mean about 90, I think. But no, we are. This is we're speeding through it. Almost, we're gonna fit it in. We're almost there.
All right,
I can get back over there and hold the mic again, but I don't know.
No, this is gonna work out.
Okay.
All right.
Yeah, it was.
So we have this weird remainder in B, and all this K here, and then the A. I'm gonna tell you something that was really simple and like we're gonna manipulate these shapes, and eventually we're gonna get a K that was a square. K that is a square, like we did in case 2.
We're gonna get a K that is a square.
Yeah, remember we got.
We're gonna manipulate the R so that the K is a square, but the K was a square in case 2.
Remember case 2? K was equal to a square.
A squared.
So we got to find a square that K is equal to.
Why? Now, is that part of the original theorem that K was a square?
Yes. K has to be a perfect square.
Oh.
So in geometric terms, we have to find K equal to.
So it didn't even have to. I thought K just had to be a number. Like we got it to be 4, but it had to be it's the fact that it was a square number was a big thing. Okay.
Yeah. So.
Oh.
So not every number will give a K for if you plug in a number for A and B, a positive integer for A and B. Each one won't give you a positive integer K. But when it divides it, that's the definition. If it divides it evenly, and you get a positive integer for K, each time it's going to be a square. But we don't know how.
Interestingly, I just got the thumbs up on my camera, which was off screen.
Okay.
Yes, I don't know. It didn't. So yeah, you just never know where the thumbs up will appear.
Well, you must be doing something right. So, long story long, as my friend Kahune likes to say, we'll just add an R square to each side because we wanna do something with this R.
All right, so now we got some excess B minus R.
Yeah.
A squared equals B minus R now? Is that right?
Yeah, A squared plus R squared equals R squared plus B times R plus K.
Oh, that plus K, damn.
Yeah, damn K. Now let's move the R over here because we have R width here.
Yeah.
So then we end up getting A squared plus R squared is equal to B plus R times R, and then plus K of these 1 by 1s. All right. Wait a second. We still got B and we got A over here. But what's B plus R, Darko?
B plus R. Brr.
You can take a minute and think about it. We had it earlier.
B plus R.
Yeah, it's been obfuscated by all of these squiggly lines, but A times K.
Oh, it was
is
it was A
actually
times K.
B, and then plus the remainder.
AK. Okay, so
Yeah.
now we got we can replace B plus R with
Yeah.
AK,
Yeah.
and then the area of that thing is now arc.
That's right. Or car. So
Rack.
this is R. An R by A times K rectangle. But what if we made
Yeah.
it an
Just for the
What if
viewers
we-
at home, we were just making jokes based on that. You multiply those three, the A, the K, and the R. You can put them in any order that you want to. So you could car, AR. You know, you're multiplying them.
yes.
You're making 3-letter words out of those
based
three.
on the commutative property of
Yes,
multiplication.
yes, an endless source of mirth and good humor. Okay,
Yeah, and
that,
fundamental axioms.
that jokey commutative
Of
property.
arithmetic,
Yes,
yeah.
okay.
So, because we can change that around to any funny word we want with 3 letters, this is also, we can make this R times K of A.
Okay, so
So
yes.
basically what we did was we had a bunch of, we had K of these R times A rectangles, and they were all added horizontally, but we took them apart. It was like and then we sliced a piece of bread up and then moved all the pieces in together like this and put them together in this direction.
Okay,
Does that make sense?
sort of. I mean, I'm just imagining. 3 times 5 is the same as 5 times 3. There's more to it than that. Maybe some distributive stuff going on.
Well, you have all these polygons, these quadrilateral, these rectangles. So you have K of them. You don't know what K is, but if you just take one and instead of adding them all like this, what if you just add them like this? So you take them from like this, and then you put them all together like that, like dominoes.
I see. So at first there are ARs, and there's K of them, and now that you took you cut them down to size and moved them that way. It's kind of the multiplication when it's vertical is it's
It's
A
times K.
K
It's actually K of A times R.
R. So those are little ARs.
Here you have K of RA. Same
Holy,
thing.
holy, yeah. All right. Okay. Yeah. You just gotta stare at it. Yeah.
Yeah.
You just gotta stare at it.
Okay. Where's that eraser at?
How is math similar to a beautiful woman? Just gotta stare at it. No, that's not what you're supposed to do.
You're supposed to respect it.
I mean, damn right.
Okay. So, are you convinced that this rectangle can be transformed into this rectangle?
Yeah.
Can I use this as an eraser?
Yeah. So we're on case 3 for those scoring at home.
Case 3.
Case 3.
But now we have a squared plus r squared equals r times k. Basically, r times a plus 1, and we have k of them.
Mm-hmm.
Let me rewrite that a little bit. little bit more recognizable. A squared plus R squared is equal to K of A times R plus 1.
Yeah. Yep. Yep.
And does that look familiar to you?
So it's like the original problem had. Oh, so R is B? R is equal to B?
No. Because R is smaller than B.
But then we got a contradiction because.
This is like the little R right there.
But am I not looking at that formula that's the same thing as the original formula, but with R having replaced B?
Yes, you are. But what we did was we subtracted B squared from each side. So there is no more B squared. But then we added R squared to each side. And it just so happened that we were able to arrive at our old equation by subtracting B squared and adding R squared.
But then what was case? So case 1 said that A plus. What was case 1 again?
Case 1 was a contradiction.
Yeah, no, but what was the setup?
The setup was that we were trying to determine
AK is less than B, right?
Yes.
AK is less than B. So isn't this R? Oh no, the R squared is. So R squared should not fall into that. Okay, I was thinking. All right, trying to think of. Never mind. Okay, keep going.
No, it's
AK is
correct.
less than B. AK is more likely to be less than B when B is replaced by this little R, right?
A times K is still greater than B.
It's more likely to be greater than B, I should say.
No, it is. That's the only way you can have this R, which we used R for remainder when you
Right.
subtracted the B squared from each side.
Right, but I'm saying when we yeah, I guess. And what I was saying was though, if you replace B in the formula with R, then AK should be all the more greater than B, because now B is just little R. But like I said, it's just it's just sort of wordplay. That's wordplay more than anything else. I don't know that.
Yeah.
Yeah, it means
What kind
anything.
of fun words can you
I don't know that it means anything.
What kind of fun words can you make out of the 4 letters?
I mean, car. Just
Bark.
distribute that, and you have car plus K1. You know,
B?
car plus K1 down on the bottom, right?
Yeah, sure.
Carl was what it looks like, you know, or Carol.
Yeah.
It's a love letter to Carol. Is this a love letter to a woman named Carol?
Yeah.
Or a man named Carol?
From a lark.
I feel like there are men named Carol.
Who is Carol? So it feels like we're down quite a rabbit hole right now.
Yes, yeah. Have we made progress?
I think so.
Okay.
I think we have.
Well, let's continue making progress then.
But this is very confusing because we kind of arrived at our original situation.
Yes.
But we subtracted a B squared, and then we added an R squared to each side.
Mm-hmm.
So that means that Felix is right in the same place where he was.
Mm-hmm.
Because we don't know how large to draw this rectangle.
Mm-hmm.
Because of K. We still don't know K.
Mm-hmm.
So this K times R times A, it could be, it can't be smaller. It can't be case 1. We ruled that
Right.
contradiction. But it could be case 2, or it could be case 3.
But case 3 is getting us this weird recursion type of thing going on. So what do we? Can we do anything? Do we have any solution to that, or are we just in a perfect circle around it?
Well, it could go on indefinitely. So we know that case 3 can go to either case 2 or case 3.
Well, that's a weird statement.
Yeah, so I'm going to call this, let's just call this whole process a function.
Okay.
And then, so from A and B, we got A and R.
Uh-huh.
And so this function is V for Vieta. So we can either go to case 2 or case 3 now.
So just I made that such noise because Vieta was a mathematical term I heard used on one of those videos we watched. Like it's an actual thing. So it's a thing. Okay.
Yeah.
Vieta.
We did the same thing that they did on the video, but we just did it with squares and rectangles.
Okay. All right.
So as you mentioned, we have like this sort of recursive thing that could happen indefinitely. Like, what if you just keep getting a smaller and smaller R? So we know that. Let me go back to this. So what do we know now? We know that case 2 is good. It ends up providing K with a perfect square. Case 3, it just gives us there's just smaller and smaller numbers. You have B, A, R, and then it would find another one. You would just keep going to case 3, and you would just get smaller and smaller numbers. Smaller and smaller remainders. From the process of...
That's the Vieta process?
Yeah. So what you're subtracting B squared. You're left with
some R.
A split rectangle here. It's R times
And then
B.
trying to find the R.
Yeah,
All you know about that R is that it fits the original equation.
Yeah, it fits the original equation.
Okay. Fair enough. So R is like B in a weird way.
Yes. In that it satisfies the equation of...
Does that mean R is greater than A?
R is less than A.
Because R is less than A, but that's weird is because
remember you had this...
But so that when we were looking at the equation, we had A squared plus B squared equals K times AB plus 1. But in case 3, or in all of them, A was less than B, right? But now A is greater than R, right? So it's like, right?
B is greater than A is greater than R. Yeah.
Anyway, go on with your bad self to the next part.
Yeah. So, yeah, remember we get to this A squared plus R squared equals K times AR plus 1. And so we're left with trying to determine is this a rectangle that is equal? In this case, it would be equal to a squared. What would happen if this? What if this rectangle? What if k times r was equal to a? That would be case 2.
Yeah. Yeah.
So you would just have a squared equals a times k times r. So then you would have k is equal to r.
Okay.
So we had a case 3. We arrived at r. And then, so if we did a case 3 and then went to a case 2, then k would equal r squared.
I thought k would equal r, but okay.
No, because this is a square. So I'll do the subtraction. So this is, so if k times r is equal to a, then this is a squared, and this is a squared. So you just cross these out, and then r squared is equal to k.
I think we need to pause for a minute and watch some Bobby Hogwalloper. This is hard. This is rough, man.
Yeah.
I'm struggling. I don't know if I can. We're not even close to the end, huh?
No, this is the wrap up.
Oh, this is the wrap up. Oh, great.
Yeah,
Okay.
This is the wrap up.
Okay.
Thank goodness, Felix. I know.
Yeah.
He's ready to jump off the building.
No, he's a happy fella. This is his whole. This is his thing. Yeah. But
you want to go back to Bobby Hogwash?
Oh, well, I'll end the video with some Bobby Hogwall.
Okay.
I think that the whole thing's gonna.
Woo! Who wants to eat some pie now after this? You're gonna need to. Refuel your.
There's Felix that you were just talking about.
Your brain insulin, your brain glycogen. So.
Yeah.
This goes to, we get the same situation where we have another rectangle and we don't know if it's case 2 or case 3. So if it's case 2, it ends up being a perfect square, and that's great. K is equal to r squared, and we know that that's a square.
All right.
But if it's not, then we have another case 3. So we repeat this whole process. And
K is equal to r squared is a sort of like affirming that we wanted to know about k anyway.
Yeah, that it's a square, a perfect square.
All right.
So if we do this though, and there's still a remainder, then we'll get an even smaller. See how this is shrinking? We'll get an even smaller r.
Oh, so you keep doing it until you get that case 2. Like getting case 2 is sort of the way that it ends. We just have smaller and smaller remainders as case 3, case 3, case 3.
Exactly. It can't go on indefinitely. It has to eventually terminate. Case 3, you can be applied repeatedly, but eventually the iteration has to terminate at case 2, and then the remainder will be 0, and then it'll be a case 2, and then you'll know what the square is. Because the thing is that each time that these are shrinking, k is staying the same. Like b is bigger than a is bigger than r is bigger than the other remainder, if there is one, if this goes to case 3, but k stays the same throughout the process.
Okay.
Yeah, so
Odd.
So
there it is.
These numbers that you find
Greater than r
smaller,
0,
but
greater
k
than
is
r1.
staying the same.
Okay. Huh. Yeah. Yeah. What yeah. I mean, it's kind of cool that we get to you can get to what is frustrating about math in a proof like this, right? Like
Yeah.
Like, do you still would you deal with frustration as you're doing it? I mean, yeah, you do. Of course you do. You know, you get stuck. You get.
Well, I still haven't found I'm still struggling to explain this. Like I wrote it down, and it took me a long time but I used a program to draw all of these squares in a rigorous proof, but trying to explain it is still, that's difficult. It's more difficult to explain the problem than it is to do it. And actually solving this problem, like actually going from this little trick where you had to like add r squared onto there, and then convert all of these vertical rectangles and stacked vertically into stacking them horizontally.
Yeah.
It took me forever to figure out. And so it was frustrating, but because it was like a challenge that I was like, I found this problem interesting. And you know, you might want to just this problem might, you know, make you question your life decisions, but there's some other problem out there that could be interesting to you, that is like a puzzle that's engaging, that you want to learn more about. And so when I was doing this problem, that's kind of how I approached it. Like, I just kept going back to it. I kept thinking about it because it was like this puzzle that I wanted to solve.
It's like keep coming back, or if this problem didn't work for you, if there's another problem out there that will. And that's right. And I just noticed, well, I agree with what you said about how the difficulty of explaining, like, and we saw it with the whiteboards, like you have to go back and forth, but like just saying words, sometimes saying words is so like, the words get totally lost. I mean, I just noticed discussing it, like I would ask a question or say something and be like, just halfway through the sentence, it's like, these words are just distracting us from the, you know, but like what's being written down on the whiteboard, there's just two different modalities in a way of expressing something.
Mm-hmm.
I mean,
yeah. And that's what we did with the problem, was we translated the algebra into geometry.
Yeah.
So that's another modality.
Yeah, both, and even like algebra, like geometry is a very spatial visual thing, but even algebra, like when you're trying to explain math, words are different than lines of algebra, you know, like, so it's, sometimes you're talking about it, but like, no, you need to see it with a whiteboard. And
and this was
not every school needs to have way more whiteboards. Like that's a real problem that schools have. They don't spend enough money on whiteboards and whiteboard markers.
That's racist. They need
my next well, that's a great point. My next sponsor is Expo. Expo markers.
Yeah.
They erase and so on. All right. Well, shoot. We're burning the midnight oil. Hey, thanks, Dale, for coming over and explaining that.
7 5 3 0 9 8 6 7 5 3 0 9 8 6 7 5 3 0 9 8 6 7 5 5 3 0 9 8 6 7 5 3 0 9 8 6 7 5 3 0 9 8 6 7 5 0 1 2 3 4 5 6 7 8 9 1 0 1 1 1 2 1 3 1 4 1 5 1 6 1 7 1 8 1 9 2 0 2 1 2 2 2 3 2 4 2 5 2